All right, so this is going to be a pretty short podcast because we're reviewing neutralization reactions here on page 6. Just make sure you have a periodic table to help you write these formulas, because that's really all we're doing here. And it's a very short top part to review some of the basics of predicting products of specific types of reactions. So when we look at these, back in Unit 7, we learned about different types of reactions: synthesis, single replacement, double replacement, and combustion. And there were a few of the double replacement types of reaction that were a specific application we called acid-base reactions. They were either acid-base or precipitation. And we already talked about precipitation reactions last unit, so we're going to focus more on these acid-base reactions this unit, which are also called neutralization reactions because the acid and the base neutralize each other. They cancel out each other's properties when they react. So just like last unit when we were predicting those precipitation reactions, this generic equation that we learned back about our double replacement reactions, this idea that the two compounds that are reacting in our double replacement reaction could be considered AX and BY. And when we mix those together, they're going to switch partners and make two new compounds, AY and BX. And that is still what's happening here. But because this is a specific type of double replacement reaction, these are acid-base reactions. Acids always start with H's. Bases are always going to end with OH's. Even if there's more than one H or OH, those are always going to be kind of our A and Y groups here. And so the first product, that AY thing that we always make, is made up of that H and OH coming together to form HOH, aka H2O, or water. So the one product you can always count on seeing on the product side of our reactions this unit is water. And then the other thing you're going to see there, the BX thing, is a salt, an ionic compound made from the leftover pieces of that acid and base that weren't the H or OH part. So the one thing you have to be extra careful of that people always end up mixing up is they try and make this compound XB, not BX, and that's not okay because the B element is a positively charged element. It was at the beginning of its original formula, and it's always going to be at the beginning of every single formula because all ionic compounds start with the positively charged piece. So make sure, even if they seem like they're closer to, like when in this reaction on this side, you see the X and then the B, you always need to make sure that whichever one is a positively charged piece, which will always be B because it was at the beginning of the formula before, always goes first. So just as a general reminder, because we're going to be writing formulas, anytime we create an ionic compound, that BX compound, we need to find the symbols and charges for the elements we're putting together from the periodic table, just based on their location, like this map shows us, reminds us. Hopefully you have those written down. If those charges don't cancel out, if it's not like a +1 -1 and a +2 -2, like just where one of each atom would cancel out and add up to 0, then we have to cross-drop reduce those charges. So remember, when we cross-drop reduce, we're crossing the charges. We generally drop the plus and minus signs at the same time. So we bring the 4 and the 2, and no more plus or minus 4 and 2. They just come down onto the opposite element. You can make this cross sign, bringing them over and down. And then if those numbers have a common factor, like this 2 and 4 do, then you need to divide those subscripts, reduce these subscripts down to the lowest possible ratio. Now, that doesn't happen all the time, but you always need to keep a lookout for it if it does happen. So I do want you to try number 2 on your own. We've done this in Unit 7. We've done something so similar to this in Unit 10 that we just finished with, and I think these are even simpler to predict than all of that Unit 10 stuff. So try this one. I will not stamp your packet if you have not at least attempted this, and then we can all talk about it and make sure that we got it right in class. But I want to see you try number 2. And I want to help you with number 3, just because it is a word equation, and you do need to be able to take names like these and turn them into formulas. We've already been talking a lot specifically about how to write the names and formulas of acids, reviewing that. at the beginning of this unit, but we also need to be able to write the formulas of bases and from words predict the products that would be formed from these things. And keep in mind, I know it seems like a lot of work, but this is the cool stuff in chemistry. Someone just saying, oh, I'm going to mix magnesium hydroxide with nitric acid. What will we make? We're about to figure that out, all from our chemistry skills with a little help from the periodic table. So we are going to find our symbols and charges of our magnesium and hydroxide. And remember, hydroxide is that OH thing we've been seeing with all our bases this unit, and it's on the back of the periodic table with its -1 charge. Magnesium's in the second column of the periodic table, so it has a +2 charge. These charges are not equal and opposite, so we're going to be crossing, dropping, and reducing. So that makes this MgOH2. An additional reminder is if we cross-drop reduce with a special group, we need to put parentheses in our formula around that special group before we put the number on it. Because without it, it would just look like we had two H's, not two OH, not two hydroxide groups. Now, when we're mixing them together, we need to make sure to put a plus between our formulas, and then we can move on to nitric acid. Remember, all acids start with H's. If this was a hydronitric acid, then that would just be H and one other element, probably nitrogen here. But because this isn't a hydro acid, this is not a binary acid, it's got one of those special groups from the back of the periodic table, right where we found hydroxide. And because this is nitric acid, it came from the 8 version of that polyatomic. So we need to be looking for nitrate on the back of the periodic table, which is NO3 with a -1 charge. So when we cross-drop reduce that with the H and its +1, well, we don't even really need to cross-drop reduce. They're equal and opposite, so we just need to put one of each together. And that's our nitric acid. Now moving to the product side, remember that this H and OH from our acid and our base, even though they're in a different order than they were in that first example, find yourself your H and OH and kind of cross them out. I'm going to actually cross them out up here and kind of turn them into this water. Actually decided instead of crossing them out, circling them kind of works. And then our leftover pieces here, our magnesium and our nitrate, are going to come together, making sure to put our magnesium first before the nitrate. And because magnesium has a +2 charge, we're going to need to cross it over onto that nitrate group, just like we did onto that hydroxide group when we put it together. And now it fits in the page a little bit better. And that's all that is to it. Now, I am going to be asking you to try balancing these equations, and so we can talk and work on that together in class if you need help with balancing. But I think you'll find, just like these are a little easier to predict the products, because of the simplicity of some of these formulas, I think that you're going to find they're also pretty easy to balance as well, just compared to some of the other reactions that we've seen. So hopefully this isn't too bad. See you in class.